Picture this, you walk into a Databricks interview calm and ready, and instead of asking you to define Spark, they slide a laptop across the table. One stage in the Spark UI is burning red. Fix it. This is what senior interviews actually feel like. Anyone can recite the docs, but seniors diagnose out loud. They talk through the driver, the shuffle, the skew, and the cost. In this lesson, every scenario gives you three things: the mental model, the proof in code, and the follow up they ask next. Let me show you how to reason like an architect. Take a look at the map for today. 8 scenarios and they build on each other. We start with the engine, then lazy execution, then wide versus narrow operations, then skew, then delta and acid, then governance, then cluster sizing, and finally debugging a slow job. But here is the secret, one thread ties every single one of them together. Spark is a distributed engine and the shuffle is where it hurts. Keep that idea in your head all day. Screenshot this slide. It is your interview morning map. We just opened the door. So let us start with the engine itself. Every Spark job has one driver and many executors. The driver is the brain. It builds the plan, schedules the tasks, and holds your Spark session. The executors are the hands. They run tasks on partitions of your data. In parallel, think of a head chef calling orders to a line of cooks. One person coordinates, and many cook at once. And here is the line that makes interviewers nod. Collect pulls all the results back to the single driver, and that can run it out of memory. Remember that because the very next question depends on it. So they lean in and ask the follow up. Why does the driver run out of memory? The answer is almost always the same culprits. Collect to pandas and huge broadcasts all land on that one driver node. The fix is not more memory. The fix is to stop pulling the whole dataset to one node. Write your results to a delta table instead. Or use take of n when you just want a peak, never collect a billion rows. Say that out loud and you sound like someone who has actually been paged at 2 am. Here is a fun one. Picture a junior who says my code ran instantly but nothing happened. That is not a bug. That is Spark working exactly as designed. Transformations are lazy. Filter, select and join, just build a plan. They do not touch your data. Nothing runs until an action forces it. Count, write, show, collect, those are the triggers. It is like writing a recipe versus actually cooking. The recipe is instant but cooking takes time. And laziness is a gift. Because Spark optimizes the full chain before running it through Catalyst. Now, the follow up that trips people up. Why is my job recomputing the same thing over and over? Because each action reruns the whole lineage from the source. Lazy evaluation has no memory by default. So if one data frame gets hit by many actions, you cache it once, cache or persist, and Spark holds it in memory. Look at the code on screen. We build the data frame called cache, then reuse it across several actions. But here is the gotcha that wins the point. Cache is itself lazy. It only materializes after the next action runs. Now we hit the heart of every Spark conversation. Narrow versus wide operations. A narrow operation like filter or map lets each output partition read just one input partition. No network, pipelined and cheap. A wide operation like group by join or distinct pulls from many input partitions. Data has to cross the network. Picture the kitchen again. Narrow is each cook working their own station. Wide is everyone passing plates around the room. That crossing of the network is the shuffle. And the shuffle is the most expensive thing Spark does. So they ask, kill the shuffle in a big join, here is the move. You are joining a huge fact table to a small dimension table. Instead of shuffling both sides, you broadcast the small one. Look at the code. We wrap the small data frame in broadcast and Spark ships it to every executor. Each executor then joins locally, zero shuffle. That is a real speed up, not a trick. But say the gotcha 2 only broadcast what fits in executor memory. Broadcast a big table and you run that executor out of memory. Here is the scenario that separates the seniors. They tell you one task takes 10 times longer than all the rest. That is data skew. One key, often a null or a single mega customer, holds most of the rows. After a shuffle, that key lands in one giant partition. So one task does all the work while the others sit idle. Picture 9 cashiers standing free and one line with 500 people. The total time is the slowest line, not the average. That is the whole point. Stage time equals the slowest task, never the average. Let us talk partitioning because the count matters more than people think. Too few partitions and you lose parallelism with giant tasks crawling along. Too many and you drown in scheduling overhead on tiny tasks. Look at the code. Repartition of n reshuffles your data evenly, but it is a wide operation, so it costs a shuffle. Coalesce of n only merges partitions with no shuffle, so reach for it. When you want to reduce, and here is the gotcha worth saying. Partitioning a data frame in memory is not the same thing as partition by on a disk write. One shapes compute, the other shapes your files. Now, a classic, how does Delta Lake give you acid on a plain data lake? Start with the problem. Plain Parquet on object storage has no transactions at all. Delta adds a transaction log on top of those files. Every commit writes an ordered JSON entry into the Delta log folder. Readers only ever see committed versions. Think of it as a bank ledger sitting over your files. Every change is an atomic recorded entry, and here is the line that lands. The log, not the folder listing, is what defines the table. That one sentence tells them you actually understand Delta. So the follow-up is the scary one. Recover a table, someone just broke a bad merge, wiped half your rows an hour ago. You stay calm because Delta has time travel. Look at the SQL. Select star from sales version as of 12 or timestamp as of a date. You read any prior version of the table instantly. That is a career saving feature. But say the gotcha vacuum permanently deletes old files past the retention window. Once you have vacuumed, time travel can no longer reach them. Here is one people fumble, managed versus external tables. And why Unity Catalog? A managed table means Databricks owns the data files. So drop table deletes the data too. Gone. An external table means you point at a storage location you own. Drop removes the metadata, but the files stay right where they are. That difference has saved and destroyed real production data. And Unity Catalog governs both with one permission model across the whole workspace fleet, catalog, schema, table, central grants, lineage, and audit all in one place. Now they make it practical, size this cluster, and should it auto scale? The answer depends entirely on the shape of the load. Steady, predictable batch work wants a fixed cluster. Spiky or unknown load wants auto scaling with a min and a max number of workers. Auto scaling adds workers when tasks pile up and removes them when things go idle. You pay for what is actually running, and Photon, the vectorized engine, can speed up your SQL and data frame scans, but always benchmark your own workload. The rule is simple, right size to the work, not to the data size. Here is my favorite. This job ran 4 minutes yesterday and 40 today. Debug it, do not guess. Step 1. Open the Spark UI and find the longest stage, not just the longest job. Step 2. Read that stage's task matrix is the max far above the median, that is skew, or is it one giant shuffle? Step 3. Check the input size. Did the source data grow or did a small files explosion hit you? That is the whole method symptom, then the metric that confirms it, then the cause. You are reading the evidence, not throwing memory at it. Let me show you the small files problem because it bites everyone. Thousands of tiny files become thousands of tiny tasks, and then scheduling overhead dwarfs the real work. The usual culprits are streaming, writes, and over partitioning. Look at the SQL on Delta you run optimize, and it compacts those small files into bigger healthy ones. Many runtimes will also auto compact on write for you. This is the difference between a job that crawls and one that flies, and naming it in an interview tells them you have lived in production. Let us talk money, because architects always do. You pay for cluster uptime. An idle interactive cluster left running overnight is pure waste, burning cash for nothing. The hidden cost is the one nobody sees. Unnecessary shuffles and full reloads that should have been incremental. So set auto termination on your interactive clusters and prefer jobs clusters for scheduled runs because they spin up, do the work, and shut down. Saying this in an interview signals something important. You think about the bill, not just the code. Now, let me hand you the framework for any scenario question. First, name the layer before you propose a single fix. Driver versus executor, memory versus shuffle versus storage. Second, say the symptom, then the likely cause, then where you would confirm it. And confirm means a specific Spark UI metric, not a hunch. Third, give the fix and then the trade off. Broadcast the table, but only if it fits in memory. That pattern works on every question they can throw at you. Symptom cause proof fixed trade off. Calm and structured beats fast and lucky. Take a screenshot because this is your cheat sheet. Engine one driver plans, N executors work and you never collect to the driver. Lazy actions trigger execution and you cache the data frames you reuse, shuffle wide operations, cross the network, so broadcast small joins, fix queue and right size your partitions. Delta, the log gives you acid and time travel and optimize cleans up small files. Tables manage drops, the data external does not and Unity catalog governs all of it. That one card is most of a Databricks interview. So let us bring it home. Every answer today traced back to one single idea. Spark is distributed and the shuffle is where the cost lives. Hold on to that and you can reason through scenarios you have never even seen. But reasoning is the start, not the finish. To truly own this, you build it for real in the full Databricks complete platform course linked below and subscribe for the deep dives on Spark tuning, Delta and the Lakehouse. One last thing, the toughest scenario you have ever been asked. Drop it in the comments, I read everyone.